The purpose of this video is to go over how to write each of these types of nuclear equations for radioactive decay and how to check to make sure they are correct. So in number 1A, you need to write the alpha decay equation for polonium-210. So alpha decay is the release of basically a helium nucleus. It's the release of 2 protons and 2 neutrons. It breaks off from the polonium nucleus and comes flying out. And then whatever is left over after that helium nucleus breaks off is the final atom, the final new isotope of that decay. So I start with polonium-210 and I draw my arrow, and the arrow is like the equal sign. So on the other side of the equation, I have 2 pieces. I have the alpha particle, which is a mass of 4, atomic number of 2, because it's got 2 protons and 2 neutrons, giving it a mass of 4, atomic number of 2. I'm using He, the helium symbol, to represent it, because any nucleus with 2 protons is a helium atom. And then the other piece, when this polonium kind of breaks apart and releases the alpha particle, the other piece that's left over is lead-206 over 82. So the mass is 206 and the atomic number is 82 and the element is lead. So when polonium undergoes alpha decay, it changes into a lead atom. So the actual identity of the element changes. So whenever you have a nuclear equation or you have a nuclear change, that's what happens. You get a new element as a result with a new atomic number sometimes and also a new mass sometimes. So to check to make sure this is right, I basically have 2 addition problems that I'm solving. I have the top addition problem, so 206 plus 4 equals 210, so that's correct. And then 82 plus 2 equals the atomic number of 84. So I have to follow the law of conservation of matter. So all of the particles that I have on the left-hand side, all the protons and neutrons, need to add together to equal the 2 separate nuclei and their protons and neutrons added together. You can't lose any mass or gain any mass during a nuclear change. At least according to the equation. You have to account for all of the particles. So in number 2, we have some beta decay equations. Beta decay usually happens in isotopes that have too many neutrons. But the principles are the same. Whatever element I'm starting with, it's going to release some kind of a particle and change into a new element. And if I add together the masses on the top and the atomic numbers or the charges on the bottom, they should add to equal the original atom. So here we have carbon-14. It's got 8 neutrons and 6 protons, so it does have too many neutrons, and that makes it unstable. So it's going to undergo beta decay, which means a neutron is going to release a beta particle, and that neutron will turn into a proton. So I have 1 more proton here than I started with. But the mass stays the same because that neutron just changed into a proton, so the total number of particles stays the same. So if I add together the 7 positive charges and the 1 negative charge from the beta particle, I get the 6 over here. And then if I add together the 14 and the 0, I get this 14 right here. So 7 plus negative 1 is 6. 14 plus 0 is 14. So basically what's happening here is carbon-14 is releasing a beta particle and decaying into nitrogen-14, which has a more stable proton to neutron ratio. It's a 1-to-1 ratio. In number 3, we have some electron capture equations, and this is where I originally had them set up incorrectly in your first worksheet, so I had to send you the email to change that. So the difference between electron capture and all of the other equations is you start with an isotope and you're adding an electron to it. Basically, this nucleus is pulling in an electron that's just outside of it. But the principles still apply. The arrow is the equal sign, and you still have these two addition problems on the top and on the bottom. So we need to make sure that they do, in fact, equal each other. So 106 plus 0 equals 106. And 47 plus -1 equals 46. So when this silver atom sucked in this electron, one of the protons changed to a neutron. So the mass stayed the same. The number of protons dropped. And we got a new element here. The element with 46 protons is palladium. So electron capture is set up differently in that you have the addition problem on the left side of the arrow, and then you have your arrow, and then you have your new element formed on the other side. And that's different from up here. You can see on the left-hand side of the arrow is the one unstable nucleus on the left-hand side of the arrow, and it's breaking apart into a beta particle and an oxygen nucleus on the other side of the arrow. So equal sign is over here on the left-hand side of the equation, and in electron capture, it's over here on the right-hand side of the equation. Okay, positron emission is also a decay equation that happens when you have an isotope that is neutron poor, just like electron capture. So you start out with an isotope that doesn't have enough neutrons. And what happens is it releases a positive particle from a proton, and that proton turns into a neutron. So the mass doesn't change, but the number of protons has gone down. So we still have to check and make sure everything's equal on both sides of the arrow. So 116 equals 0 plus 116, that's correct. 50 equals 1 plus 49, so that's correct. And this new, more stable isotope is the element indium. So on the back side of this worksheet, you just had to fill in the blank based on looking at the structure and looking for clues in the equation to determine what type of decay, and then use your math skills, your adding and subtracting, to figure out the answer. So 0 plus 14 is 14, -1 plus 7 is 6. So the isotope that starts this equation is carbon-14. And it's decaying into nitrogen and a beta particle, and that makes this beta decay. In this last part of the worksheet, you are analyzing the isotope and determining what type of decay it might undergo. So we're starting out with thallium-212, which has 81 protons and 131 neutrons. So 131 divided by 81 gives you about 1.6 neutrons for every 1 proton. So this is an isotope that has too many neutrons. The atomic number is less than 83, so it's not necessarily going to undergo alpha decay, although it could. But because it has too many neutrons and it wants to reduce the number of neutrons for every proton, it's most likely going to undergo beta decay. So I start with my thallium-212. 212 is the mass, 81 is the atomic number, or the charge if you think of it that way. Here's my equal sign, here's my beta particle, and then whatever is left over for my new nucleus needs to add together on the bottom and the top to equal my original starting nucleus. So 82 plus -1 is 81, and 212 plus 0 is 212. There are only 2 neutron-poor isotopes in this table, and it doesn't matter to me if you write them as positron emission or electron capture equations, because both of those types of decay will increase the number of neutrons.